Hello and welcome. We're going to study self-adjoint operators in this little module. So, here's the definition. An operator T from Fn to Fn, right, is said to be self-adjoint if T equals T star. Now, this is a very interesting constraint, T equals T star, self-adjoint, as in the operator itself is equal to its adjoint. And it turns out to have really powerful properties, a lot of applications which we will see later on. But for now, we will study what this means if the operator became its adjoint itself. So, the first question you may ask is this even possible, right? So, at least from a definition point of view, it's not too bad, right? So, T is a operator from Fn to Fn. So, T star is also an operator from Fn to Fn. It's got its range and null and all that, and maybe T could be equal to T star, right? So, it's not impossible. If this N and M were different, then this is never possible. So, because it's the same, maybe this is possible. But let's look into it a bit more closely and figure out, can we easily generate operators or matrices of operators which are self-adjoint? Okay. So, is this possible? That's the first question. It's actually, you'll see it's quite easily possible. So, supposing you start with a matrix A, right, n by n matrix, and look at its Hermitian. A Hermitian is row and columns are transposed, and everywhere you do conjugate, right? So, it becomes A11 to A1n, AN1 to AN1, right? So, this is easy enough to see. Now, if T is going to be equal to T star, right? So, you assume that this A and A Hermitian are with respect to some orthonormal basis. So, that if A represents T, A Hermitian represents T star, right? So, the orthonormality of the basis is important, otherwise then A Hermitian will not represent T star, right? So, we know that. So, we will assume that this is with respect to an orthonormal basis, okay? So, A and A Hermitian. So, if T has to be equal to T star, then all you need is A to be equal to A Hermitian, right? So, that's it. If A becomes equal to A Hermitian, then you're okay. So, if you look at the ijth element, here it is Aij, right? The ith row and jth column. Now, if you look at the ith row and jth column here, first of all, there's a transpose. So, you get Aj, the same A here, but Aj. It will be jth row and ith column, right? If you want ith row, jth column, you have to go to jth row, ith column, find the Aj there, and then also conjugate it, right? Because you do transpose and then conjugate. So, the ijth element here is Aij, while the ijth element here is Aj bar, okay? So, if you want these two to be equal, we require Aij to be Aj bar for all ij, okay? When you pick this matrix A, you have to pick its elements such that Aij equals Aj bar, okay? This should be true for every ij. So, how do we satisfy this? Can this be satisfied? Yeah, it's not too bad. First of all, let's look at the diagonal elements, right? When I is equal to j, the condition you need here is Aii equals Aii bar, okay? And now that is easy to satisfy. You simply choose all the diagonal elements as real. You can pick them to be any real numbers. Any real number you can pick for the diagonal elements, they will satisfy this condition Aii equals Aii bar, okay? What about the other guys? The other guys, you divide and conquer, right? So, you look at the upper triangular part where the row index is less than the column index, I is less than j, that is the upper triangular part. You select that arbitrarily, it can be any complex number. So, the upper triangular part, so the diagonal part you have to pick to be real, and then the upper triangular part, when I is less than j, you can pick as any complex number, whatever number you want you can put there, okay? And then all you have to do is to make sure that the lower triangular part, once you have picked the upper triangular part, the lower triangular part when I is greater than j should easily be set according to this equation. So, you have to set Aij to be Aji bar, okay? So, you take the upper triangular guys, do the transpose, do the transpose and conjugate it, you will get this condition satisfied, okay? So, very simple self-adjoint condition. So, I hope you see and appreciate how this has come about, okay? So, basically it's conjugate of the transpose element, okay? So, if you pick like this, you will always end up with a self-adjoint matrix. So, you can come up with self-adjoint matrices, this matrices which have the self-adjoint property quite easily, right? So, pick diagonal to be real, and then the upper triangular arbitrarily, and the lower triangular will simply be the transpose of the upper triangular part, transpose conjugate of the upper triangular part. So, it's possible you can create a whole bunch of self-adjoint operators. Now, self-adjoint operators, like I mentioned, are truly special. They have some really powerful properties. But before we see that, let's just see a few examples of how this is working out, okay? So, here is a bunch of examples. and you can quickly identify this one. The first one is not, they cannot represent a self-adjoint operator. The second one is clearly self-adjoint. Now, this is a special case where every element is real. If every element is real, all you need is the matrix to be equal to its transpose. So, the diagonal can be arbitrary real, but then the upper triangular part, once you pick that, the lower triangular part is already fixed, right? So, 2, 0, 0, then 2, 0 comes here, and then the 0 comes there, okay. So, here you have complex numbers, it will be slightly careful, the conjugation is not respected here. It looks close to being self-adjoint, but for I have I here, but then I need to conjugate it, so I'll have minus I instead of just I here. So, note this down, this is an important little change here. This one, for instance, is self-adjoint. So, the 2 represents self-adjoint, 4 represents self-adjoint, 3 does not, and 5 also does not. It looks like it is close to being symmetric, but then the diagonal is not real, okay. So, you have I here, when you conjugate, it will become minus I, it will not be equal, okay. So, you see here for 2 and 4, the Hermitian of these matrices is equal to the matrix itself. So, A equals A Hermitian is satisfied. For 1, 3 and 5, for various reasons, it is not satisfied, okay. So, the second problem is also slightly interesting. So, a matrix is given A, B, 1, 0, and it is with respect to a particular basis. Now, 1, 1, 0, 1 is the basis. You notice here this is not canonical, okay. So, it is very important to note this is not a canonical basis. So, it's saying that this represents a self-adjoint operator. A lot of people will look at this and say this cannot be a self-adjoint operator because it's not symmetric, right. So, this part is not equal to this part. So, it cannot be self-adjoint, but then be careful about it because this is not with respect to an orthonormal basis. It's with respect to some other type of basis. So, first thing you have to do is convert this A into orthonormal basis, say canonical basis. So, you know how to do that. You know how to change basis for a matrix. You do that, you will get some other matrix, and then you look at the condition A equals A Hermitian. You will be able to find this value, okay. So, a little bit of an exercise. It needs first conversion from this basis to the canonical basis, and then you look at the condition A equals A Hermitian, and that will give you a self-adjoint operator situation, okay. So, note this kind of thing down. It's very important. This A equals A Hermitian holds. A Hermitian represents T star only when you are working with a orthonormal basis. So, that's an important criteria to remember, okay. So, I hope this sort of convinced you that self-adjoint operators are plentiful, right. There are enough of them out there, and they do have very interesting properties. So, we are going to see 2 of the most important critical properties which make self-adjoint operators so powerful and have so many applications, okay. So, first the 2 properties relate to eigenvalues and eigenvectors of self-adjoint operators. The first property is sort of interesting, is the eigenvalue of a self-adjoint operator is real, okay. So, if you remember, for an arbitrary matrix, you will have to solve a polynomial to find eigenvalues, and then that polynomial may have complex roots. Even if the matrix has real entries, the polynomial may have complex roots. We have seen several examples of that. Now, if the operator is self-adjoint, if the matrix has that adjoint property, A equals A Hermitian, then the eigenvalue has to be real, okay. So, this is a powerful property. Here is a quick proof. I am going to quickly walk through the proof. So, you start with an eigenvector which has an eigenvalue lambda, right, and it's self-adjoint. And then you look at this Tv comma V. So, most of the proofs in this self-adjoint operator world will start with this. It will start with Tv comma V. Now, if you look at Tv comma V, Tv is lambda V, right. So, this on one side lambda V will come and the lambda will come out of the first operator. And then what do you do for the other side? You do the adjoint, right. So, you equate this inner product to V comma T star V. Now, T star is equal to T, okay, and then Tv now comes on this side, which means you will have a lambda V. But lambda is on the second operand of the inner product, second argument of the inner product, so it will come out as lambda bar, okay. So, you have lambda Vv equals lambda bar Vv. Now, V is an eigenvector, so it is non-zero. So, you pull it to this side, you have lambda minus lambda bar, Vv is 0, now Vv is non-zero. So, lambda equals lambda bar. So, now lambda equals lambda bar is the same condition as saying the eigenvalue is real, okay. So, quick proof to show. So, that is okay, that is sort of interesting, but what is even more interesting is this wonderful property for eigenvectors. So, eigenvectors of distinct eigenvalues of a self-adjoint operator are orthogonal. Now, if you remember, for any operator, the eigenvector corresponding to 2 distinct eigenvalues is always linearly independent. Linear independence is guaranteed just by the eigenvalue being distinct. Now, this does not need any inner product or anything, it is always true. Now, if you are in an inner product space and you have a self-adjoint operator, If the eigenvalues are distinct, then the corresponding eigenvectors have to be orthogonal. Okay, so that's a strong constraint. It comes from the self-adjoint property. It puts this very strong constraint of orthogonality for distinct eigenvalues. So the proof also goes along similar lines. I'm not going to spend too much time. I'll just go through very quickly. V and U are two eigenvectors with two eigenvalues lambda mu, and then you start with T v comma u. The same story here, lambda v u, and then it will go to the other side. T is self-adjoint, right? So it will become v comma T u. Then mu v, mu will come on this side. Why is it mu and not mu bar? Why should I not say mu here? Because mu is real, right? So these are eigenvalues of self-adjoint operators. They're all real. There's no need to write mu bar here. It's just mu. Now you have this wonderful equation. You pull it to this side. Lambda minus mu, Vu is 0. Now this gives you the result you want. If lambda equals mu, Vu can be anything. If lambda is not equal to mu, then V and U have to be orthogonal to each other. Okay, so wonderful property for eigenvalues, eigenvectors of self-adjoint operators. So here are two examples. I'll urge you to try this example very closely. I think we did do it earlier, so I'm not going to do it in great detail. You can go back and check and find all the eigenvalues and eigenvectors of this matrix and check that whenever the eigenvalues are not equal, the eigenvectors will end up being orthogonal. The same thing has to be true here. It has to be true. So you can check that these eigenvectors and eigenvalues are orthogonal to each other. Okay, so you may be able to find the eigenvalues here. So we saw how to find eigenvalues here. If you want to find eigenvalues for this guy, 3 is immediately an eigenvalue, right? 0, 0, 1 is an eigenvector and 3 is an eigenvalue. So you see here that comes out very nicely. And here it may not look apparent to you now, but actually if you multiply this second guy by minus I, right? The second column, if you multiply by minus I, you will get the first column. Okay, so the first and second column are linearly dependent. So you will get one of the eigenvectors to be something, right? So you will get 0, right? I'm sorry, one of the eigenvalues is 0, right? So 3 is an eigenvalue. So these two columns are linearly independent. So null space is non-trivial. So 0 is an eigenvalue. So you have to find out one more, and you can use the trace if you want. So trace is 5. So one eigenvalue is 3, another eigenvalue is 0. You can find the third eigenvalue and proceed, right? So it's sort of interesting how you can do these problems in such nice ways, and you'll get good answers. Okay, so I hope you see how these things work out. You can check for everything that the eigenvalues, the eigenvectors corresponding to distinct eigenvalues are orthogonal. Okay, so that's this example. Okay, that concludes this little module. Thank you.